Okay, so I've used this task loads over the years now in various different ways, from visiting primary schools and using it with their year 5 and 6 pupils. I've used it loads of times in teacher CPD sessions as well, and more recently, and the focus of this video, is how I used it to introduce simultaneous equations with year 11 students. So the idea is simple. You've got a cat on top of a table and a tortoise down below, and you can see the distance there. And then the cat and the tortoise switch position, and you can see how that distance decreases. And the question is simply, how tall is the table? So have a pause and a think if you've not already, and then we'll go through the task in detail next. So I love this task then because on the face of it, it looks quite simple, but when you actually try and go and solve it, it often gets people stumped, and some people jump straight to an algebraic approach. But there is a really nice simple solution which just uses a bar model. So the important thing to remember is that the heights of the table, the cat and the tortoise are all constant. They never change. What does change is the distance between them when the cat and the tortoise change position. Now, we can draw bar models for this using rectangles, but for the sake of this video, I'm actually going to use cues and air rods because it's really useful to actually move these bars around to get to the solution. So I'm going to model this. I'm going to use the brown rod for the table, which makes sense. And I'm going to use a psychedelic pink cat, and I'm going to use a green tortoise. So there's the first scenario where the cat is on top of the table. And this distance here is 130 centimetres. Now in the second model, remember, and all these heights stay constant, the cat jumps down, tortoise gets scared and jumps up to the top of the table. And this distance reduces to 50 centimetres now. So there's the bar model. You can draw it out if you want, but I just think it's more powerful to be able to move these rods. These are just lengths, and traditionally when we draw a bar model, we normally have it horizontally instead. So I'm not changing anything by just moving these rods around like this. It's just more familiar to see a bar model in this format. This length is still 130, this is still 50. Now the nice things about lengths is that you can always just add them together. So if I take the top model and add it to the bottom model, I end up with this long length on the top and this long length on the bottom. Remembering this gap is still 130, this gap is still 50. And the top length is equal to the bottom length. Now doing that often is enough to prompt a solution from pupils now. Others you might have to say, well, you can add lengths in any order. Addition is commutative. So instead of going table plus cat plus table plus tortoise, I might choose to do table plus cat plus tortoise. That's still the same length. And similarly, on the bottom length, instead of doing tortoise plus 130 plus cat plus 50, I might decide to do the 130 and the 50 first, and then add on the cat and the tortoise at the end. So this distance here is the 130 plus the 50 now. So this distance here is 180. And once the model's in this format, you can clearly see that two of the tables is 180 centimetres, so one of the tables must be 90 centimetres. Okay, so going back to my year 11s then and how I used it with them, well, it was to give an understanding of what happens when you add equations together when solving simultaneous equations. So I gave them a little bit of freedom here to choose their own animals. So I said choose a scary one and a less scary one, but make sure they've got different letter names so we can model it. And also I don't want them beginning with T. So we've got this T for table here, and we settled on a lion sitting on top and a frog down below. And I made them choose their own distance as well. So we said, let's call this 100 centimetres, say. And then for some reason, the lion gets scared of the frog, so they switch position. So this scenario happens where the frog's on top, and now the lion is down below. Now we agreed that the lion's probably taller than the frog, so this distance is going to decrease. And again, I let them choose their own. Let's call it now 40 centimetres. So we set up a similar model, but with their own animal, their own values, so they're a little bit more invested in the problem now. And again, what's the height of the table? Can we work it out? Now, because we'd drawn the models and they were used to it, when it came to writing this as an algebraic equation, a more abstract equation, it made sense to them. We've got the table plus the lion, and when I subtract the height of the frog, I get this distance of 100. So let's write that down. The height of the table plus the lion minus the frog is equal to 100. And then the lion gets scared and the frog jumps up. In this second scenario, we've got the table plus the frog minus the lion is 40. So the table plus the frog minus the lion is equal to 40. And at this point, referring back to how we added these two lengths together when we solved it originally, we can just add these two equations together now, and that will give us another way of getting to the solution. Remember, when we used the Cuisenaire rods, we added them together and we could shift around the lengths. The same kind of thing is happening here. When we add these two equations together, we end up with the length of two tables. So you end up with 2t. The lion plus the negative line, if you want, we've got a zero pair going in here, they cancel out just like they did in the original model, and the frog and the negative frog, they cancel out together as well. So we end up with the height of two tables as being 140 centimeters. So one table in this scenario would be 70 centimeters. And then we did a few examples like that, choosing their own animals and their own heights, until we could generalize the problem. And pupils eventually noticed that it doesn't matter whatever these two heights are, essentially you just end up adding these two heights together and then just dividing your answer by 2. So here we've got 140 divided by 2, the height of the table is 70, and on the original problem the height of the table was 90, it was just 130 plus 50 divided by 2. So, hope you've enjoyed that, and as always, any comments and thoughts, post in the thread below.